Regarding the experimental setup of the photoelectric effect experiment, over here we have two different compartments. We have the vacuum diode compartment, which consists of a cathode and an anode, and over here we have the hydrogen light source, which is going to be incident on the cathode plate of that vacuum diode compartment. Then over here in the middle we have the cutoff filters. So we have different cutoff filters actually, and each cutoff filter is going to correspond to a certain wavelength. So whenever you rotate the outer part of these cutoff filters, you are basically changing which color you are allowing to pass from that hydrogen source and to be incident on that cathode plate. So over here, for example, we are allowing a light of a wavelength of 546 nanometer, and we are filtering out the rest of the colors. And then behind that cutoff filter over here, we have none other but the aperture. So the role of the aperture, as we have seen before, is actually to cause light to undergo diffraction. So light which is coming from that hydrogen source and being filtered through that cutoff filter is actually undergoing diffraction once it reaches that aperture of 8 millimeter. And over here, by rotating that part of the aperture, we can change the diameter of the apertures from 8 millimeter to 4 millimeters and finally to 2 millimeters. So for each trial, we are going to be varying with the diameter of the apertures. And like I said, the role of the aperture would be to cause light to undergo diffraction and therefore be incident on the cathode plate. So let's say that we are starting with an aperture of 4 millimeters, for example. And then we want only to allow the light which has a wavelength of 405 nanometer to pass through that aperture and be incident on the cathode plate. Now let's have a look over here on the other side of that experiment. So over here we have an external power source. So as we have seen before, the role of the external power source would be to apply a reverse potential or a stopping potential to the initial potential which is established between the cathode and the anode within that vacuum diode compartment. So down below over here we are reading the value of the reverse potential that is being applied, and above we are reading the value of the photoelectron or the value of the electrical current. What we need to do in that case, we need to vary with that amount of the potential difference applied or with the amount of the reverse potential applied until that amount of the electrical current drops to zero. So over here you are going to rotate the knob of that reverse potential and you are going to keep an eye on the amount of the electrical current applied. So we have to rotate it the other way until the amount of the electrical current drops to zero. So over here we almost got to 0 amps. So basically now what we have done is we have matched the amount of the potential difference that is being established between the cathode and the anode with that reverse potential that we have applied over here. So over here we have reached a certain value for the reverse potential of 0.78 volts. So we can still manipulate it a little bit until the current perfectly drops to zero. Okay, so over here we have reached an amount of 1.04 volts for the reverse potential applied, for which the amount of the electrical current is actually zero. So basically we have matched the potential difference that was initially established between the cathode and the anode within that vacuum diode over here. Now we have to repeat the same thing all over again, but for a different cutoff filter. So now we are going to rotate that outer cast, and let's say now we are using a certain wavelength of, or we are using a certain cutoff filter of a wavelength of 436 nanometers. So now we are allowing only the light which has that same wavelength to pass through that aperture and to be incident on that cathode plate. So if we have a look over here, so since we have changed the wavelength of the cutoff filter, therefore over here the electrical current is no longer zero. So whenever you are changing the cutoff filter, meaning now you are allowing different color of light to pass through and be incident on the cathode plate, in that case the electrical current which was previously scaled down to zero now is no longer zero, simply because we have a different color of light being applied to that cathode plate. So what you are going to do in that case, all over again, you are going to vary with the reverse potential until the amount of the electrical current drops to zero. And now we are at 0 amps all over again, meaning we have perfectly matched the amount of the potential difference that was initially established between the cathode and the anode for a certain color of light that was incident on that cathode plate. And then the same thing is going to be repeated for the other cutoff filters of 546 nanometer then for 575 nanometer, and finally for the 395 nanometer. That would be for the 4 millimeter aperture. Then you have to repeat the same thing all over again now for a different aperture. So over here, let's say you switch to 8 millimeters, and then you are going to be switching all over again from one color of light to another by varying these cutoff filters. And for each cutoff filter, you are going to vary with the reverse potential applied until the photoelectron, or until the electrical current which is established between the cathode and the anode drops to zero. And we are going to see later on that the diameter of the aperture, it has no effect on the value of the reverse potential applied. It is actually independent of the value of the reverse potential applied.